these next couple of slides just talk a little bit about what regulates the production of stomach acid. And there's some of it is controlled by hormones that get released, and then some of it is actually controlled by the brain, by the central nervous system. So when we talk about gastric secretion, so stomach acid being released, there's 3 phases to that. There's the cephalic phase. What does cephalo mean? Head. So this is going to be anything coming from the head, right? Like seeing food, smelling food, thinking about food. All of those things cause you to start making more gastric juice, because when you do all of that, when you smell food, you think about food, your brain goes, oh, we're getting ready to eat, right? So that's one thing that will initiate gastric secretion. We also have a gastric phase. What does that mean? What's gastric? Stomach. So this one makes sense. When food gets to your stomach, you make more stomach acid. Okay. And then the last phase is the intestinal phase. This is when the chyme gets squeezed from your stomach into the intestines. But this last phase is not really going to cause you to make more gastric juice. It's actually going to turn it off. Okay, so I like to say that the cephalic phase and the gastric phase, I'm going to put a plus there because they're turning it on. But the intestinal phase mostly is turning it off. Okay, now, in reality, all of these phases can either turn it on or turn it off, but I'm just giving you the predominant actions of each of those phases. So the cephalic phase, again, this one's coming from the head. It's smelling food, thinking about food, looking at food, and it is predominantly what we call excitatory. It's going to turn on gastric secretion. It's getting ready for you to eat some food. But there is a slight negative or inhibitory secretion, things that might cause you from the cephalic phase to turn off gastric secretion. This would be things that, you know, if there's ever a time where you just lose your appetite, right? Like stress, emotional upset, depression, a lot of times that is going to come with a loss of appetite, and that causes you to turn off gastric secretion. So sometimes there can be an inhibitory effect, but usually that's from an imbalance. Okay, so usually it's going to be excitatory. The gastric phase is when the food gets to your stomach. This is going to make the most of the gastric juice. It makes some sense, right? Just because I'm looking at food, like maybe I'm watching a commercial with a hamburger on it, I'm not going to pump out tons of gastric juice because there's a chance I'm not going to eat anything. And so when food actually gets to your stomach is when you're going to make the most gastric juice to help you break it down. So this phase will last about 3 to 4 hours after you put food in the stomach. It makes the majority of your gastric juice, about 2/3. And it's predominantly excitatory, right? You are releasing a hormone called gastrin that causes you to make more stomach acid. The other thing that causes you to make more stomach acid is when you put food in your stomach distends, it gets bigger. That's going to cause more stomach acid release. And when you put food in your stomach, you change the pH in there. What's the normal pH of gastric juice? 1. What happens to it when you add food to it? It starts to go up. It becomes more basic, right? And so by changing the acidity, or by adding proteins, or even caffeine, right? You've probably heard of people say that when you drink caffeine, it actually increases your metabolism a little bit. It's actually causing you to make more gastric juice. This is also why they used to think that when you drank too much coffee, it would cause stomach ulcers, because you're making too much gastric juice, right? We know that's not necessarily true. But these are all the things, when you get food in the stomach, when your stomach distends, when the pH changes in your stomach, those are all the big triggers that cause you to make more stomach acid. Things that in the gastric phase that can turn it off are things like stress and fear and anxiety. Again, that's usually going to be associated with an imbalance. And then the intestinal phase, this is going to help to control the emptying of the stomach so that it happens slowly. And so this is why I told you that when you start putting food, that chyme, into the intestine, it's going to turn off gastric gland secretion. You don't need more stomach acid. So it is mostly inhibitory. And so what causes it to be inhibitory is the presence of chyme in the intestines, presence of an acid in the intestines. That makes sense because chyme is an acid, right? It's food mixed with gastric juice, which has a low pH. And the presence of an irritating substance. I would say that acids are an irritating substance, right? So all those kind of go together. When that happens and you get that into the intestines, that's saying, hey, slow down, release this chyme slowly, and we can turn off gastric gland secretion. There is a slight and excitatory effect. This is right when the food gets squeezed into the small intestine. There's a little bit of gastrin release right then, but for the most part, I don't want that to confuse you. For the most part, it's what I start. It's inhibitory. Okay, it's turning everything off. We're done with the stomach. Okay. If there's ever a time that you squeeze chyme into the small intestine too fast, that's called dumping syndrome. It's usually caused by eating really sugary foods, carbohydrate-rich foods. Sometimes it can cause a lot of nausea and vomiting. And it's really common in people who've had gastric bypass. So when people have gastric bypass, a lot of times they have to go through, before the surgery, they have to go through counseling to learn how to eat correctly, the amounts and the portions that they should be consuming, what kinds of foods, what kinds of macronutrients are the good kind of food that they should be consuming. Refined carbohydrates should not be part of their diet, okay, because it can cause this dumping syndrome. I had one of the secretaries at the University of Alabama when I was there had gastric bypass, and so this was like 20 years ago. It was a really long time ago. Not quite 20 years ago, but it was a really long time ago. So it was a relatively new procedure. She had it done, and afterwards, when she made it back to work, I don't know, a month or so later, she went out to lunch with some coworkers, ate all the wrong things. She was coming back in the building up the stairs. She got so sick, so nauseous that she passed out and fell down the stairs from it. And that's from that dumping syndrome. This is just a visual of those three phases, right? So you can see the cephalic phase, and I like the visual because it shows the brain. So it's everything coming from the brain. Looking at food, thinking about food, smelling food, and even tasting food. And that's going to turn it on. So this is mostly stimulatory. And you can see it's driving stomach secretory activity. The gastric phase is shown you here when food is in the stomach. So that's distension of the stomach. It is peptides or proteins in the stomach. It's changing the pH of the stomach. All of those things are also going to turn it on. And then you can see the intestinal phase has a picture of the intestines. And this is when chyme gets in the intestines. So it's distension of the intestines. It's the presence of an acid in the intestines. And all of that's going to turn it off. Okay? No. So vomiting is called emesis. This can be caused for a whole lot of reasons. One is stretching of the stomach can cause vomiting, so eating too much. And then also, anytime you get an irritant in your intestines, so this could be bacterial toxins, excessive alcohol, spicy food. Sometimes people will say, whatever I ate didn't set with me well. That's usually, it's that spicy food, alcohol, even certain medications. I remember once I was on an antibiotic and it was really strong. And for some reason, like, I always read the pamphlet and always make sure that the pill has the number or the symbol that it says it's supposed to have on it, and make sure that there's no pharmacy error. I have a friend who works in the public health school at UAB. He's the director, and he says that the fourth leading cause of death in the United States is medical error, whether it's at the hospital or because you've been given the wrong medication. So I always check. I always check my pamphlet. I always check the pills, make sure it's right. And the pamphlet said, take these antibiotics on an empty stomach. So I did. Oh, it was bad. I got so sick. And so I did it like you take it in the morning, you take it at night. And I did that for like 2 days. And finally I called my doctor and I said, I can't take this medicine. I can't keep it down. And the nurse said, well, are you taking it with food? I said, no, the pamphlet says don't take it with food. She says, oh, you got to take that with food. That'll really hurt your stomach if you don't. So there are definitely drugs that can really upset your stomach. Whenever you vomit, this actually is caused by the signaling of an area of your brain called the medulla oblongata. That's one of the vomiting centers of your brain. This one does not have a blood-brain barrier, so if you get toxins in your body, it sends a signal to the medulla and says, we got something in here that should not be in here. You need to vomit and get it out. When you vomit, you empty out the entire contents of your stomach, and you also start to empty out the small intestine. You empty out the first part of the small intestine, which is called the duodenum, and the second part of the small intestine, which is called the jejunum. Now the problem is that when you excessively vomit, if you cannot keep fluids down, it'll cause severe dehydration and an electrolyte imbalance. Because when you vomit, you are losing a lot of stomach acid. It can actually cause a change in the pH of the fluids in your body. So this is why it's really important if you are vomiting excessively that you try to stay hydrated. In little kids, we give them Pedialyte. Pedialyte has those lost electrolytes in it, and it gets absorbed really quickly. So if a child takes a drink of Pedialyte and it only stays down for 2 minutes, they've absorbed a little bit out of there. So I want to make it through the small intestine because you're looking at that today, and there's 3 parts to it, which a lot of times students get confused on these 3 parts. This is the organ that is involved in finishing digestion, which again is breakdown. Because remember, we talked about how by the time food gets to your stomach, you haven't broken macromolecules into their monomers. So your small intestine is going to finish that job, and you're going to absorb those monomers. So it's involved in digestion and absorption. And the small intestine is 2 to 4 meters long from the stomach, from the pyloric sphincter of the stomach, all the way to the ileocecal valve. That's the ending of the large intestine, the small intestine, where it dumps into the large intestine. So the 3 divisions are the duodenum. It's the first part of the small intestine. It's about 10 inches long. The jejunum is the second part. This is the majority of your small intestine. And the ileum. And this is the last part of the small intestine. Now the reason that we have an ileocecal valve, and I mentioned this to some of you when you were doing the rat, you could see this on the rat. So when you look at the intestines of the rat, there's an area that's really big and it's filled with air. And I don't know why, I think they gas them, I don't know what happens, but it always fills with air, and that's always the cecum. And that is always the beginning of the large intestine. And so where the small intestine and the large intestine come together, we have the ileocecal valve. Because the end of the small intestine is the ileum, the beginning of the large intestine is the cecum. So ileocecal valve. Yeah.
Which part was the majority?
Jejunum.
Why is it this?
Oh, I don't know. I think. Here we go.
Oh. That makes sense.
Yeah. All right, so when we look at this image, you can tell that the majority of this in here, this is the jejunum, and you can see this is all the large intestine up here, or sometimes we call it the colon. So the first part of the small intestine isn't super long, it's the duodenum. And the duodenum is, in the duodenum, this is where the food leaving the stomach, or chyme, goes into the small intestine. So you're not only going to have that opening from the stomach in the duodenum, but you also have an opening from the gallbladder. This is called the bile duct. This is coming from the liver, from that gallbladder. And you also have an opening coming from the pancreas, called the main pancreatic duct. And you're going to look at these in lab today. Those 2 things, those 2 tubes come together and dump into the duodenum. And they form, where they come together, something called the hepatopancreatic ampulla. That makes sense. What does hepato mean? Liver. Pancreatic is pancreas. So this is a tube that's coming from the liver and from the pancreas, and it's dumping into the duodenum. We're going to talk about this But in reality, what's happening is in the duodenum, you've got this chyme, right? We have not broken everything down into monomers yet. So we need to finish the breakdown in the duodenum. We got to do it early in the small intestine because we need the rest of the small intestine for absorbing nutrients, okay? So early in the duodenum, we want to add bile, which is coming from the liver. Does anyone know what bile does? What does it help with the breakdown of? Anybody have a gallbladder removed? Everybody has their gallbladder? Do you know anyone who doesn't have a gallbladder? Is there anything they can't eat?
It's like a lot of starchy type food, isn't it? Like greasy food. Yeah.
Greasy food. When you don't have a gallbladder, you can't really eat a lot of fried food because bile coming from that gallbladder helps you break down lipids. So you're going to squeeze bile into the duodenum so that you can help to break down lipids. And coming from your pancreas is super important. Not only does it release insulin, which helps with blood sugar, but it releases amylase, lipase, protease or pepsins, and nucleases. It releases an enzyme for every one of these major macromolecules to help you get them into their monomers. So the pancreas is incredibly important for digestion. So you've got these tubes, one helping with the breakdown of lipids, and the other has enzymes for all of those macronutrients, and that's getting dumped straight into the duodenum right at the beginning of that small intestine to finish digestion. So here's a picture of that, and you are going to look at this in lab. So I have a model that looks like this. It doesn't have a liver on it. But what you see is the duodenum. So here's the first part of that small intestine. It's not very long. It's like 10 inches long. And the stomach, they took it away, but the stomach would sit like right in here, right? So we're going to squeeze from the stomach, we're going to squeeze the chyme into the duodenum, and right here is the hepatopancreatic ampulla. You can see this one's coming from the gallbladder. It's carrying bile, helping with fat breakdown. This one's coming from the pancreas. It's got enzymes for all those macronutrients to help with the breakdown. Now, the last couple things that I'm going to mention today is I just want to talk about when we look at the small intestine on the inside, it's kind of special because the job of your small intestine is to absorb. Anytime you got to absorb nutrients, you want a really, really big surface area so you can absorb the most possible out of that food. So the ways that we increase the surface area is folding the inside of the small intestine. When you get folds, you get a greater surface area. So to give you an example, if we start, let's say I have a line here, right, and that's the surface area. I could take that line and I could go from here to here, but instead of having a straight line, I can do this. Now, if I were to take that string and pull it out, this is a lot longer than this one, right? It's a greater surface area. You can do the same thing, but now I can do folds on top of folds. It's the same thing, it's going the same distance, but now this surface area is greater than this one, right? And then I could even, and I can't show you these, but I could even put microscopic folds in there too, and the surface area would be even greater. That's what we do with the lining of our intestine, right? So we start with big folds called circular folds. And these circular folds, these big ones, actually help the chyme. Instead of going straight through the tube, they make it do this, like it's swirling down a toilet bowl, kind of. And so that's helping to get all the nutrients out of that chyme so that all parts of it are seeing the wall of the intestine. But it's also increasing surface area. We have villi, which would be like this. So these would be like the circular folds. These would be the villi. They're the folds on top of the folds. These are going to create, if you were to cut open the small intestine and look at it, The inside of the small intestine looks like a velvet shag rug. It's really soft. That's because of those villi in there. So that's increasing the surface area. And then microvilli, we also call these the brush border. These are microscopic. These are tiny little projections on the surface of the cells. These are also increasing the surface area. But they also have some enzymes and release enzymes to help with macromolecule breakdown. So here's a picture where you can see the big folds in here, these big folds. Those would be those circular folds, right? And they're helping with the food swirling down. And then you have villi. You can see those villi, like I drew on the board. And then you have microvilli, which you can't see in this picture. But I like the picture on, let me move this out of the way, if I can. Put it up here. I like this picture down here because you can actually see the texture of that small intestine. And it really does look like carpet. It's really, really soft because of those villi. So this one is showing you the brush border. So this is showing you the microvilli, which again, they're microscopic, which means they're on the cells. And we talked about microvilli in AP, whoops, move that down here. We talked about microvilli in AP1, where you have on the surface of those cells, not cilia, but you can have invaginations to increase the surface area for absorption. Okay, the last thing I'm going to mention about our intestines are something called intestinal crypts. Just like you have gastric pits, you have pits in the intestines. And these have a lot of cells that secrete substances in them. Just like in the gastric pits, you've got cells that release substances. And the cells that we find in our intestinal crypts are listed here. You have, just like in the gastric pits, enteroendocrine cells. What does endocrine mean again? Do y'all remember? Hormones. So these are going to release hormones. You have intraepithelial lymphocytes. You know what a lymphocyte is, right? It's a white blood cell. So it helps to fight infections. So these are some white blood cells that are going to be found in that small intestine. And the job is they kill off infected cells. Get rid of them. Makes sense to me. You are putting foreign things in your mouth and then you absorb stuff. So you want to have white blood cells right there where you're doing the absorbing so that you're not pulling something into your body that you don't want in there. Okay. And then we also have a type of cell called a Paneth cell. These are releasing things like human defensins, lysozymes. These are all broad spectrum. They're going to kill off foreign organisms. And then the last thing is that the lining of your small intestine has a lot of stem cells in it. And you will, just like the lining of your stomach, you will replace the lining of your intestinal epithelium about every 2 to 4 days. So it's replaced a little bit faster than the lining of your stomach. You're constantly replacing that lining. One thing I want to mention, has anybody known anyone who's ever had to go through chemotherapy? Yeah. What are the symptoms that you remember? Do you remember? Nauseous? Yeah, that's a big one. When people go through chemo, they get sick, they get nauseous. Tired. A lot of times their hair falls out, but also like their skin will get really, really dry. My cousin had breast cancer and went through that. So I would always just send her lotion and care packages so that she could keep her skin hydrated. And I want you to think about what all that has in common, right? The lining of your stomach, the lining of the intestines, your skin. It's all the same tissue, right? It's epithelial tissue. In epithelial tissue, those cells divide really quick, which is great because when you're healthy, if you cut your skin, you heal it quick. If you get damage to the stomach or the intestines, you heal it really fast. But if you think about what chemotherapy does, chemotherapy is a whole body cancer treatment, right? You get it, it's your whole body. And chemo is a drug that targets rapidly dividing cells, which are what cancer cells are, but so are epithelial cells. So this is why when people go through chemo, they lose their hair, their skin gets dry, the lining of the stomach just gets obliterated, which is why they get so nauseous and they vomit so frequently after chemo. So that's why we see chemotherapy taking such a toll on epithelial tissues when people have to go through this treatment.